All right, thank you very much. My name is Christian. This is why you should consider Haskell for your next production system. A little bit of background about this talk. This talk is an adaptation of a post on the Foxconn Systems blog from January of this year, titled Why Haskell is a First Choice for Building Production Software Systems. The post was widely read and positively received. We received over 16,000 unique readers, spending a total of 66,000 minutes reading the post. The post hit the front page of Hacker News. The contents of this talk will overlap with the post, but the details are different. If you read the post, you'll still get something from the talk and vice versa. You will find this talk most valuable if you're evaluating Haskell for use in a production system at your company or organization. You're considering using Haskell for building software that has practical applications and want to understand its strengths. You know very little about Haskell, but want to learn more about why one would use it. Or you're skeptical that Haskell has practical applications, but are open to being convinced otherwise. A little bit about me. I started programming in around 2006. My first experience with programming was writing some IRC scripts, tweaking forum software for some of the gaming communities I was a part of. Starting from 2010 and in 2014, I studied computer science at UIUC. In 2011, I had my first experience creating commercial software that was for a small gaming company that monetized several game servers. I was responsible for adding or working with a team, adding features and content for players. In 2014 was my first time using starting web development professionally, using languages like PHP, using Node.js and jQuery. This is at this company, I would go on to become the CTO. So I spent a long time at this company. In 2015, it was the first time that I started learning Haskell. Haskell is something that appealed to me for its promises of improved productivity, type safety, and some of the guarantees that turns out are true. That's why I'm giving this talk today. In 2016, I had the opportunity to convince my team to try using functional programming for our production system. We started with Elm. We'd later go on to using Haskell. And then in 2020, I co-founded Foxconn Systems. A little bit about Foxconn Systems. We started Foxconn Systems in 2020 based off of the belief that we could build software that's a lot better than what's out there for a lot of people. The goal is to build software that's fast, secure, and reliable. Haskell is one of the first tools that we reach for, as it helps us achieve these goals and hit all these points very well. We've used Haskell for a variety of things, from typical CRUD backends for SaaS software to services for payments processing, and even the static site generator that our company website is created with is written in Haskell. That being said, Haskell is not the only tool that we use, because it's not always the right tool for the job. When it isn't the right tool, we use what is. We often write about Haskell and application performance or application performance optimization on our blog, which you can check out at that link. So, why should you consider Haskell for your next production system? Haskell has a strong static type system that prevents errors and reduces cognitive load. In other statically typed languages, the compiler can feel like an annoyance. By contrast, Haskell's compiler feels like an invaluable pair programming buddy that gives instant feedback. There's a far smaller cognitive load that needs to be maintained when writing Haskell than when writing other languages such as Python. Many concerns can be completely offloaded to the compiler. We don't have to ask questions like, do I need to check whether this field is null? What if fields are missing from the request payload? Has this JSON string already been decoded? What if this JSON string can't be decoded? Will this operator implicitly convert this integer to a string? Are these two values comparable? The Haskell compiler takes care of all of these types of concerns for us, and it uses the type system to perform these checks to give us the assurances that, for example, the JSON string has already been decoded, that these values aren't comparable, and a whole series of checks are performed at compilation time. Haskell uses type signatures to convey information about functions. This is an example of a function definition in Haskell. The function is called add1, has parameter x, has one parameter x, and then the body of the function is x plus 1, so it adds 1 to the whatever x is. So if we call add1 on 1, the return value is 2. If we call add1 on 100, the return value is 101. So the type signature of add1 is int to int, meaning it takes one integer and it returns an integer. So suppose we have an arbitrary function named my function. The signature here is int bool. My function, therefore, takes 2 arguments. Arg1 and arg2 are both integers. We don't need to see the implementation of my function to have strong guarantees about what the function does. Importantly, the signature int bool tells us a lot about what the function doesn't do. It doesn't decode JSON. It doesn't make database or HTTP calls. It doesn't manipulate strings. We can assume that it takes 2 numbers and compares them. So for example, we might see this signature int bool in a function called isEqual. And the implementation of isEqual might be 2 parameters, x and y, and the body of the function might just be x double equal y, meaning just a comparison of whether they're the same value. Type signatures can also be polymorphic, represented by lowercase type variables. The signature ABA tells us that the function takes 2 parameters of arbitrary types and returns a value whose type is the same as the first parameter. But this feels a bit limited. Can we have a type signature that conveys more information? Haskell has a feature called type classes, which are type interfaces that enable code reuse. For example, the signature num_a, ABA, tells us that A implements the none type class, meaning that it must be a type that supports operations like addition, subtraction, and multiplication. Earlier, we looked at add1, whose signature there was just int to int. Now, if we were to change add1 to, instead of being int to int, be A to A, but include a num_a type class constraint on A, we could implement add1 the same way. The body of the function is identical, but now we can call add1 with an integer, or we can call add1 with a float. Before, when the signature was int to int, the second add1 of 1.5 would be a compiler error. But that being said, we still cannot call add1 with a Boolean. We cannot call add1 with a string because string and bool are not instances of the num type class. We can even leverage tools like Google to search for functions via their type signature. Suppose that we want to check whether an element in a list is in a list of elements. What does the signature look like? So suppose we have an element of type A, and then we have a list of elements of type A indicated by the square brackets. And we're asking the question, is this element in the list? So the return value is true or false. If we use Google, we'll find that it points us to the lm function. Haskell is a pure functional programming language lending itself to reliable and composable code. Purity in this sense refers to code that is said to be pure or free of side effects. This property is known as a referential transparency and is true of any expression that can be replaced with its return value without changing the functionality of the code. This is only possible when functions do not have side effects, such as creating files, running database queries, or making HTTP calls. Let's consider the following JavaScript code. We declare a variable, user age, set it to 10. We call a function isEven on user age, and we wrap that in an if statement. And if the return value of isEven is true, then we log the user's age, or log the user's age as even. Otherwise, we log the user's age as odd. Can we replace the call to isEven with its return value without changing the result of the code? Well, that depends. Can we trust the implementation of isEven? For example, the implementation of isEven might be exactly what we expect. We just return the number mod 2 and whether that is double equal to 0. But is this actually the case? What if the implementation does something else? What if we log? What if we have some malicious code running? What if we have more side effects? We print to the screen, we produce alerts, and then we still perform the same action. JavaScript doesn't enforce purity. We have no guarantees that isEven or any function has no side effects. In Haskell, purity is enforced by the type system and side effects are controlled. The signatures we saw earlier, such as int, bool, were all pure since the return values are primitive types like bool, int, float, string, and so on. Any function that performs I/O actions, such as printing to standard out, reading a file, or anything else, must have a type signature that reflects this. For example, the main function, which we see in Haskell programs, has a signature of I/O and then unit. The open parentheses, closed parentheses is referred to as unit because it's a stand-in, it's not a real value. The implementation here is just our hello world program. So this is put strlen hello world. So because this produces a side effect, the type signature is IO. Now, thinking or extending this a little bit, if we think of a function with the signature of file path to IO string, this indicates that the function takes a file path and performs an IO action that returns a string. Google shows the read file function has exactly this signature if we search for file path to IO string. In Haskell, higher order functions enable composability. Higher order functions are functions that take other functions as parameters. fmap is one of the most commonly used higher order functions, which applies a function to each value in a container that can be mapped over, such as a list. So let's look at an example. Suppose we have a function square. Square is takes an integer and returns an integer. So square is implemented as we take one parameter x, and the body of the function is just x times x. So we are raising the integer that we get to the power of 2. So if we now use square in conjunction with fmap on, say, a list of integers, the return value is the result of applying square to every single element in that list of integers. But this example isn't very interesting. Let's look at another. So we'll look at more data types later, but for now, suppose we have a user data type. The user data type has 2 fields, ID, which is an integer, and name, which is a string. With this data type defined, we can create user values. For example, we have user ID 1, who is John, user ID 2, who is Jane, and user ID 3, Simon. Let's keep these 3 users in mind. So now let's write a function for displaying a user in HTML. We'll call the function render user, which takes a user and returns a string. The function is implemented as we see here. Just a special note: this square bracket pipe syntax is called a quasi-quoter, and we're using this to write non-Haskell syntax directly in our Haskell code. In this case, this particular quasi-quoter lets us interpolate values from the outside. So we're interpolating the username and the user ID in a similar manner that you might see in other languages, such as Ruby. We can use this function to turn a user into HTML. For example, if we call render user on user 1, which we defined earlier, the result is the following HTML, where we see a div with the ID UID1 and a name John. The thing is, we have a list of users. We have user 1, user 2, user 3. How can we turn them all into HTML? Essentially, what we want to do is we want render user 1, render user 2, and render user 3 all inside of the list. But the thing is, we can't really do this. I mean, we can, but the problem is we might have an arbitrarily long list of users. Our list of users may come out of the database. It may come out of, we may receive it from the request body or whatever other source. So because of this, we need some way that doesn't involve writing render user in every element of the list. So we can reach for fmap. If we call fmap and we give it render user and then our list of users, which could be 3 users or it could be 1,000 users, we get a list. The type of this list is a list of string, and every element in the list is the HTML of the user generated by the render user function. But in order to make this useful, there's one more step. We need to combine these into a single HTML string. So let's extend this example just a little bit. So we're going to take the same expression, fmap, render user, and then our list of users, and we're just going to wrap it in concat. And what concat does is it will concatenate every element in the in a list using whatever means is implemented for concatenation for that type. So in this case, it will just append all the strings together. So the takeaway here is that higher order functions such as fmap make writing composable and reusable code easy. We can write render user in terms of a single user and can easily use it for a whole list of them. Through the combination of static types and pure functional code, developing software in Haskell tends to be very fast. With Haskell, we don't need to rerun the program or refresh the page after every little edit to find out whether there are issues with our code. We can instead lean on the type system and the compiler for feedback. The common workflow relies on a tool called GHCID. GHCID relies on the Haskell REPL to show us feedback immediately after saving changes. For example, here on the left we have Vim and on the right we have GHCID. So here we make an edit to our code, we save, and then we immediately see GHCID says that we have an error, we couldn't match the expected type text with actual type int. So when we change our code, we save, all good. As you can see, this is a very, very fast feedback loop. We see whether we have an error immediately after saving our file. And speaking from experience, more often than not, if it compiles, it works. Many of the errors we encounter while writing code that can be caught during the compilation include syntax errors, misspelled function and variable names, type errors, and the immediate feedback that we get from a tool like GHCD allows us to fix these far more quickly. And the fact is, a lot of the errors we encounter while writing code will fall into these three categories. If say we're writing JavaScript or PHP or whatever, we oftentimes, in order to validate that our code is correct, we have to go to our browser or go to our program and actually rerun it, refresh the page. With GHCID or tools like it, and the type checking that occurs statically at compilation time, we catch a lot of these errors a lot faster. Compile time type checking also makes refactoring Haskell code easy. Changes that would be a nightmare in dynamically typed languages are very easy in Haskell. Many refactoring initiatives involve making the desired change in one location and then fixing each compiler error one by one. This allows a Haskell codebase to change and grow without fear of introducing regressions. We're going to look at an example of this type of refactoring a little bit later on. Proponents of dynamically typed languages will sometimes argue that automated tests supplant the need for compile time type checking. However, for tests to be effective, they must actually be written, make correct assertions, be comprehensive, meaning test a variety of inputs, provide good coverage, meaning test a large portion of the codebase, be easy to run and finish quickly, because we all know that slow tests aren't going to be used, and be updated and maintained in tandem with the code. Haskell's type system doesn't actively require any of the above. The type system is a fixture of Haskell. The compiler always validates that types are correct. The type system is inherently comprehensive, validating that types and not values are correct. It provides full coverage of every piece of Haskell code. There's nothing to update as the underlying code changes. All this is not to say that the type system can replace every type of test. Sometimes we are still going to be in situations where we can offload a lot of these concerns to the type system and to the compiler, but we may still want to write tests that test our business logic. There's things that we will not be able to model in our type system, and that's when we want to write tests. But it does provide assurances that are more comprehensive than tests and are present in every Haskell code base, even when no tests exist. Haskell programs compiled by the GHC compiler are extremely fast. When compared against other languages commonly used for application development, such as PHP, Ruby, or Python, Haskell can be at least an order of magnitude faster. Critics of performance comparisons will argue that the cost of hardware is relatively small compared to the cost of programmers, but order of magnitude performance differences between languages add up. Here's a real-world example. In one system we worked on in the past, we began implementing new API endpoints in Haskell instead of the existing PHP. After about a year, the services were dealing with a similar average workload in terms of request count and type. They performed similar CRUD actions backed by the same SQL database, and both were hosted on Amazon EC2 instances. Here's a breakdown of the infrastructure we used for each web service. The instance types for PHP were C5XL, and for Haskell were T3 Nano. The CPU for each of the PHP servers, we had 4 dedicated cores. For Haskell, we had 2 flex cores, meaning they were limited to 20% use and could only temporarily burst above that point. We had 8 gigs of RAM for each of the PHP servers, and then 1/2 of a gig of RAM for each of the Haskell servers. The monthly cost per PHP server was $122 and was $3.75 for each Haskell server. We had 2 PHP servers and 4 Haskell servers for a total of $244 a month for the PHP infrastructure and $15 a month for the Haskell infrastructure. Our Haskell service costs roughly 1/16, or about 6% of what our PHP servers cost to operate. According to our AWS metrics, the Haskell machines never even hit 5% CPU usage and consistently had response times of well under 100 milliseconds. The service in question had 25,000 monthly active users, and costs were $200 a year for the Haskell service and $3,000 a year for the PHP service, for a savings of $2,800 per year. This isn't a huge amount of money, but the difference in cost and scale is the size of the user base, the number of MAUs, and the underlying infrastructure increased. And one other important thing to note here is that if we choose Haskell because we believe in its productivity benefits or whatever else, we get this performance benefit for free. The Haskell code that we wrote in this example was not optimized Haskell. We're writing in a high-level language akin to Python or whatever else you can point at, and we're still operating with such a tiny fraction of the infrastructure because Haskell is just that much faster. Haskell is great for domain modeling and preventing errors in business logic. Beyond basic compile time and type checking, Haskell enables us to model our problem domain through the use of custom data types. We're able to create a description of business logic rules through algebraic data types consisting of both records, which are product types, and tagged unions, which are sum types. We saw an example of a record earlier when we defined our user. So let's look at an example of domain modeling. Let's model an invoice system. So we're going to declare a data type invoice. Our invoice is going to be a record. It will contain several fields: an invoice number, which is an integer, an amount due, which is of type dollars, which we'll define in a second, billable items, which is a list of strings, status, which is going to be an invoice status, which we'll also define in a second, created at, which is a UTC time, which is a timestamp, and a due date, which is a type day, which is just a date. It's worth noting that if we were doing this for real, our billable items would probably be another custom data type or a list of a, say, billable item rather than just a list of string. So our type dollars is just an alias for an integer. So when the compiler sees dollars, that just gets erased and it gets replaced with integer. So there's no difference other than for us, the programmer. Our invoice status, though, is going to be a sum type. The invoice status values are going to be issued, paid, or canceled. So at a glance, this may look similar to something like a JavaScript object, but this is a type. And as a result, we get much stronger compile time guarantees. So a few guarantees that we do get by defining this in our code: we can't create an invoice that is missing an invoice number, amount due, or any other field. The status of the invoice must be one of issued, paid, or canceled, and cannot be null or undefined. And the created time must be a timestamp, and the due date must be a date. So here's an example invoice value now that we're going to create out of our type. So here our invoice number will be 1. The amount due will be 200. Billable items will be a list of strings. The string is design and programming. The status of this invoice will be issued. The created time will be the result of a function call or the result of a call to a function named created time. And our due date will be the result of a function called to from Gregorian, which helps us construct date. So we can access these fields by using the field names themselves as functions. So for example, if we call amount due on invoice 1, the return value here is going to be 200. So let's create a user notification using our invoice type. So we're going to define a function called create notification. The create notification will take an invoice and return a string. The definition of create notification, again, we just take one parameter. We're going to call it invoice. We're going to now check the status of the invoice and apply or perform what's called a case statement. So we're going to examine each possible value of the invoice status. So if the status is issued, we're going to say that or create a notification that says invoice number, and then the invoice number is due on the due date. When the status is paid, we're going to say successfully paid invoice and then the invoice number. And if the status is canceled, we're going to say the invoice number and then the invoice number canceled. So looking at our previous invoice, invoice 1 that we defined, if we call create notification on invoice 1, we're going to get invoice number 1 due on February 15th of 2022. Suppose we have an invoice 2, different values, different invoice number, different invoice status. If we call create notification on invoice 2, we're going to see successfully paid invoice number 2. Now, suppose that sometime later we get a request from our product manager. Some invoices need to be refunded. Can we add a refunded status? Sure, no problem, easy enough. Let's just update our invoice type. So we're going to look at our invoice status, issued, paid, canceled. Let's add refunded. That's it, we're done. But wait, we get an error. The compiler checks our entire code base and finds that in our file called invoice.hs, on line 15, we have a case statement. The case statement turns out that our pattern matches, meaning the examining of each possible value of invoice status, they are non-exhaustive. Patterns not matched, refunded. We didn't consider the refunded status that we just added in our case statement. So all we need to do is go to our create notification function and handle this case. So we have our create notification function that we defined earlier. We just add a refunded case. So now when the status is refunded, the notification will be refunded invoice and then the invoice number. Haskell gives us the ability to model our business domain using its type system. By doing so, we get assistance from the compiler checking that only valid states are possible and that every case is handled throughout our entire code base. Haskell has a large number of high-quality, mature, and battle-tested libraries. Haskell's package repository, Hackage, has over 16,000 packages available, and there are many more published in places like GitHub. This number is dwarfed by other more popular languages, however. Ruby has 168,000 gems. There are 336,000 Python packages on PyPy. And as of April of 2020, NPM had 1.3 million JavaScript packages. So how can Haskell measure up to these other languages? The fact is, when building production systems, we want package quality and not package quantity. The total number of packages available is largely irrelevant. We need packages that we can trust enough to stake our business on. Haskell has excellent options in numerous categories, from JSON parsing to type-safe SQL query builders to low-level networking. As a reference, here's a list of categories and libraries commonly used in each category. If later on you choose to build something in Haskell, feel free to use this slide to find a library that you're looking for. Haskell makes writing concurrent code easy. Values in Haskell are immutable by default, making it far safer and simpler to write concurrent code. In a language with mutable values, multiple threads accessing the same value can lead to issues like race conditions and deadlocks. Haskell's immutability significantly reduces the risk of these types of issues, even when a program is running on multiple threads and accessing shared memory. This also leads to a simpler mental model. Concurrent code can often be written in the same style as single-threaded code. The underlying workload can then be executed on a new thread that invokes the single-threaded implementation. So let's look at an example. So we're going to check the latest Haskell posts from our favorite RSS feeds. So we're going to start by writing a function called getFromURL, which takes a string and returns an IO byte string. A byte string is just going to be essentially just a string, the result of the web page. And what we really want is just the body of the page. So we're going to define getFromURL by taking a single parameter, URL. We're going to call out to make a GET request to that URL using a library function that we don't see the definition of here called GET. We're going to store the response that we get in a local variable called response. And then we're going to access the response body. We haven't covered the syntax, but suffice to say that we're accessing the response body and we're returning it. And again, this whole thing, as we saw earlier, is wrapped in an IO type. The return value is an IO type because get is an IO action. We need to call out to the outside world. So we need to reflect that this is an IO in our type signature. So now we're going to have another function called load RSS feeds. This is going to also return an IO. This does not take any parameters, just has a return value of IO and then a list of byte string because we're going to have a list of RSS feed contents. So the implementation of this is we're going to get from URL and then our first RSS feed, get from URL, second RSS feed, and our third one. And we're going to store each of those in local variables for this implementation. And then we're just going to return the list of them. That's it. This is real code, and the average runtime of these two functions and this code put together is 2.2 seconds. However, each request is independent, so let's make these requests asynchronous, meaning let's make all three of the HTTP calls happen at the same time, because we don't need to wait on any one of them before starting the next one. So our get from URL function is identical. This is the same as the single-threaded implementation. Our load RSS feeds function is can be have the same return type, an IO of byte string. We're going to take our list of URLs, and instead of calling each one by one, we're going to put them into a local variable, a list called data URLs. And then we're going to make a call to a function provided by the async library, which I actually mentioned earlier on the package reference slide. We're going to use for concurrently, and then we're going to pass data URLs as the first parameter and get from URL as the second. And what this is going to do is going to take a list, and we'll apply a function that returns or performs an IO action to every element in the list. So as you can see, this kind of reads like a for loop. So for concurrently, so for every data URL, we're going to get from URL. That's the implementation, and the runtime here is 0.8 seconds, down from the 2.2 seconds of the synchronous implementation that we saw just a second ago. So it's very easy to change our code from synchronous code to asynchronous code in Haskell. Concurrency is a useful tool in the Haskell Programmer's Toolkit. Its ease of use means that it can be employed for a wide range of uses. We can make asynchronous HTTP requests or database queries, similar to what we just saw a second ago. When performing slow API calls, such as sending an email, we can make the API call asynchronous without blocking a user request. So for example, when someone registers an account, we can confirm their registration immediately, have our web application respond right away, while we send an email verifying their email address in the background. We can use concurrency for asynchronous logging, meaning we can log what happens in our code without slowing down the main thread. Again, we can give our users a response faster. We can run both HTTP and WebSocket servers on the same executable. Say that we have a small or a simple program that right now we don't want to break out into separate executables. We can write Haskell code very easily that when the singular executable starts, on one port we run an HTTP server, and a different port we run a WebSocket server. One other use case of concurrency is we might implement background workers, and this might be similar to the previous point, where when we start our web server, we also want, say, a series of background workers to start, and perhaps we read in at boot time from a YAML file or some other configuration file, just defining the number of workers that we want to start. From the technical side of things, GHC, which is the Haskell compiler, provides lightweight user threads called green threads. GHC multiplexes green threads over a small number of OS or native threads. A multi-core thread scheduler can switch between threads efficiently without any OS context switches. As a result, Haskell's green threads are much lighter weight, at least 100 times lighter than native OS threads. It's easy for a modern machine to smoothly run tens of thousands of threads. If you want to read more about this and the sources of some of these numbers, the GHC wiki has a great article on the scheduler, and there's a book published online called The Performance of Open Source Applications, which talks about Warp, which is the premier Haskell web server. It's what you're going to see most commonly used in production in Haskell code bases. Haskell enables domain-specific languages, which foster expressiveness and reduce boilerplate. A domain-specific language, or a DSL, is in contrast to a general-purpose language, and this is a small language designed to be well-suited for expressing the rules of a specific application or problem domain. Many Haskell libraries improve DSLs to improve their usability. One of the most well-known DSLs is SQL, which is used to query data stored in a relational database. Unlike most languages, SQL is declarative rather than imperative. SQL describes what the outcome of a query should be rather than how to achieve it. Any developer familiar with SQL can imagine how writing code to retrieve data stored in tables as a series of rows in an imperative style would be very cumbersome. We wouldn't want to write for loops and iterate over all of our data manually, applying our filter conditions. It's a lot easier to just write select from whatever, where whatever, and know that we're going to get the correct result. One of the Haskell features that facilitates DSLs is called template Haskell, which allows embedding non-Haskell code in Haskell programs. Let's see an example of the persistent DSL for schema definition. So persistent is a library is a SQL library that helps us query data from a database. It contains a domain-specific language for defining our database schema. We can define a schema in our Haskell code using this non-Haskell syntax, this DSL, and then run it to generate all of the helpers that we need to query the database, or even run migrations, define the tables, and so on. So suppose that we have a table person. The table has, or person table has a name column, which is of type text. We have a table blog post. It has a body column of type text, as an author ID, which is a foreign key of person, so the type there is person ID. And then we have a publication date column, which is a timestamp of type UTC time. Then we have a blog post tag, because we can tag our blog posts. And then we have a column there of type text called label. And then that also has a foreign key to the blog post that it tags that is called blog post ID and is of type blog post ID. This is not Haskell code, but it can be loaded from either an external file or passed through a quasi-quoter, which is similar to what we saw earlier. In this case, the quasi-quoter will look a little bit different than the one we saw before. But for here, we could see this embedded directly in a Haskell source code file. Not all DSLs introduce their own syntax, however. Embedded DSLs, also known as EDSLs, are written in the syntax of the native language. These are common in Haskell. The Escolito library gives us an EDSL for building type-safe SQL queries. Here's an example of a SQL query written in Escolito. You can see there are many symbols here, some syntax that we haven't seen in any of the examples up to this point. But looking at this, we can kind of tell what it's doing. We can tell that this is selecting from a table, left joining into another one. We're defining an on condition. We're defining a where condition. So this matches fairly closely the underlying SQL code. DSLs give us the ability to be more expressive when writing code. Libraries that expose DSLs give us the ability to write code that is well suited for the specific domain and prevent us from having to write boilerplate or unnecessary repetitive code. So the 10 lines of the persistent DSL, where we defined our person, blog post, and blog post tag tables that we saw earlier, this supplants the need to write approximately 150 lines of Haskell code. The Escolito query, on the other hand, is very similar to the underlying SQL, except that its correctness is validated at compile time. So the compiler will actually ensure that our query is correct based off of the schema that we have defined. We all know, if we've written SQL, it's very common to write typos or have incorrect column names. This is all taken care of by the compiler. Haskell has a large community filled with smart, friendly people. One of the most important facets of using a language is the community. The community is full of people with diverse backgrounds, including programming language researchers, some of whom have been working in Haskell since its inception in 1990, creators of other programming languages whose compilers are written in Haskell, self-taught Haskell enthusiasts, and professional Haskell programmers using Haskell commercially. We at Foxhound Systems fall into this category. The community is very welcoming towards beginners. While Haskell has a learning curve that is steeper than that of many other languages due to its depth and breadth, it's easy to ask questions and find assistance from people that sincerely want to help others learn the language. It's not uncommon to see a programming language researcher take the time to help a total newbie with a basic question. There's a variety of ways to engage with the community. Here are some of our favorites. The Haskell subreddit, which has over 60,000 subscribers and is one of the largest programming subreddits. The functional programming Slack, which has a large number of Haskell channels, such as Haskell and Haskell Beginners. The Haskell Weekly newsletter, which is a weekly newsletter that highlights blog posts and other news from the preceding week. This is a great way to find out about interesting blogs and kind of other happenings related to Haskell if you don't have time to browse the subreddit or stay in chat. And then there are also Haskell mailing lists, such as Haskell Cafe and the Haskell IRC channel, which was formerly on the IRC network Freenode, now on Libera. So just to recap, why use Haskell for production systems? Haskell is a strong static type system that prevents errors and reduces cognitive load. Haskell enables writing code that is composable, testable, and has predictable side effects. Haskell facilitates rapid development, where free refactoring and excellent maintainability. Haskell programs have stellar performance, leading to faster applications and lower hardware costs. Haskell is great for domain modeling and preventing errors in domain logic. Haskell has a large number of mature, high-quality libraries. Haskell makes it easy to write concurrent code. And Haskell enables domain-specific languages, which foster expressiveness and absolve us or reduce the need to write as much boilerplate. And Haskell has a large community filled with smart and friendly people. Thanks for listening. If you have any questions or want to get in touch, there's my email, and there's a link to where you can download the slides for this presentation below.
Thank you so much, Christian, for joining us today and for your presentation. We have a couple questions, so let's jump on in. The first question says, how can I start type-driven development with Haskell?
So I think that so type-driven development is something that I think is something that you will naturally arrive at. My advice for starting this, so I would consider this as just thinking in terms of the types. So even when I was writing this invoice example in this presentation, I'm thinking in terms of the types that will allow me to model my domain or model my problem. So rather than writing in a dynamically typed languages, I don't have the ability to define my types first, but in Haskell I do. So in terms of kind of getting your feet wet with this, doing this for the first time, think about the types that you need. And then also don't worry about it too much if you get it wrong. As I said, Haskell makes it really easy to refactor. You can change your types, and then the compiler tell you where else you need to change your code and kind of what needs to be updated. That's my recommendation for starting and kind of thinking about this. But yeah, just thinking in terms of the types first, I think will allow you to then kind of naturally think through the actual implementation of, okay, what does my actual value level code have to do? But starting by defining the types first, how they're related, what I need, what my possible states are, or what my possible values are in the case of a sum type like invoice status. That I think that's a good way to start. So.
Thanks. All right. Our next question says, how can a beginner discover functions like from Gregorian, and by extension, a minimal set of functions that could be regarded as a standard library? This is a question which is building on the example you provided.
Yeah, great question. So this is one of the reasons why I really wanted to provide that slide with all the libraries. I know that is still a very long list, but so for example, in order to discover from Gregorian, I actually didn't know this off the top of my head. I had to rediscover it, so to speak, right? So I knew that I wanted a date type. I searched, using Google. I searched for date. I eventually, settled on, oh yeah, right. I need to use the time library, and the time library uses as you're looking through there. I didn't really show the examples of what happens when you click on a result from Google, but if in the time library you look through there, you'll find that the day type is used to represent dates. So whereas a UTC time is for timestamps, a day type is for dates. But then the question is, how do I discover from Gregorian? Well, because I have my day type, I can search the time library. Hackage makes it really easy to search through. You can even, when you're looking at Hackage documentation for a given library, you can press the S key, and that allows you to, a little window in your browser will pop up, allowing you to search via text, and it'll kind of auto-complete suggestions. So if you type day in that little autocomplete search, for example, you're going to start to see functions that either take a day type or return a day type as in their type signature. So if you search for day, you will find that from Gregorian is going to be one of the results. And I believe the arguments from Gregorian are 3 integers, and then they return a day. So that's kind of your suggestion that, oh, I can just pass 3 integers here and produce a day. And that's from memory, I don't think that's even the only way to produce a day. There are other ways to do it. I just happen to find and select this one, right? So, just to recap, search Google for kind of the types you want. It'll lead you to the library that you need, and then you can search within that library to find the functions that you need to produce the types that you want or the values that you want.
Great question as well. All right, our final question. What are the best learning resources for Haskell?
Yeah, so for me personally, learning Haskell was a long and kind of like incremental process. I mentioned the Haskell Weekly newsletter. I strongly suggest anybody who's interested in learning Haskell subscribing to that, because there you get a whole variety of material that you're exposed to, and that will help you discover the best sources for you personally. For example, I tried learning from books. I am not the type of person that will sit down and read a 900-page textbook from cover to cover. For me, it was more learning by doing. So, one day I was done with my toy examples. I said, I had enough of this. Let me just write a small real program, something that actually performs an IO action or whatever. This is after being exposed to enough examples, enough blog posts where I can I was able to kind of piece together from, say, some of the libraries that I knew, enough of the standard library or what was referred to as base, and so on. But so in terms of one resource, if you're looking for a book, there is Haskell Programming from First Principles. If you're looking for just what you can be exposed to, I strongly suggest subscribing to the newsletter. You're going to be exposed to a lot of material that way. You can ask questions on the subreddit. There's a Haskell Beginners subreddit as well. That is super helpful, and they will point you to the right or in the right direction based off what you need, because your needs may be a little bit different if you're doing web development versus, say, compiler development or whatever. So yeah, sorry that I don't have a super concrete answer, because I know and believe that ultimately learning resources are going to be a very personal thing. So my suggestion is look at some of these things that I mentioned to discover what the best resources are for you personally.
I think that's a great piece of advice. And also, everyone does learn differently. So something that worked for you, like you said, is probably not going to work for someone else. Yeah. Okay. Saw one last question come up here, which is perfect. So from a Java developer used to rich IDE experience like IntelliJ, what editor would you suggest to use when starting with Haskell?
So this is a great question. I know that if you're writing something like Java, you're going to be used to the IDE experience. Personally, I use, and I've seen from many others, that you use whatever simple editor you want. So in my case, that's Vim. And Vim is complicated, but it's simple in terms of its Haskell specific features. It doesn't have any. It has maybe syntax highlighting, and that's it. So I personally use Vim and GHCID, that example of the kind of recompilation that I showed a little bit earlier in the presentation. But if you're looking for something heavier weight, there is now a much more developed than used to be tool called HLS, which stands for Haskell Language Server. You can run Haskell Language Server in tandem with something like VS Code. I haven't done it myself, but I've heard positive feedback from others that have tried it, and that gives you a lot more Haskell specific kind of type suggestions and refactoring suggestions and auto completion, and the similar features that you'd get from rich IDE as we think of when we think of, say, IntelliJ. So again, my suggestion for me personally is, and for many others, is just use whatever editor you like. That can be VS Code, that could be Sublime, that could be Emacs, that could be Vim. Try GHCID. If GHCID and that workflow doesn't work for you, you want more of the IDE-like features, try HLS. Word of warning though, HLS does use a lot of RAM. You're going to need a pretty beefy computer to run it smoothly, and especially when you have a lot of Haskell code. So.
Great. What a great question too to round out the session. So thank you to whoever asked that question, and thank you, Christian, for joining us.
Thank you.
All right. I hope you get to stick around for the remainder of the conference day and into the rest of the conference tomorrow and Wednesday. And thanks again for joining us.
All right. Take care.